Good afternoon all of you. My screen is visible. Hello, anybody?
Yes,
Yes,
sir,
sir.
visible.
Well, so we'll see the third unit. This is a thyristor rectifiers. These are the contents, single phase control rectifiers. In this we have half wave and full wave control rectifiers with different loads. This is a basic question. If you understand this, remaining is very easy. Only modifications only we need to do. So only one question if you are aware, throughout the unit is same. No need to read also, just small modification and then small derivation, limits will change, that's all. In this half wave rectifier and full wave rectifier with different loads, first R load, then RL load, then RLE loads and so on. And across load we can connect one prevailing diode, and also we can find the performance difference. Similarly, same thing will move on to three-phase control rectifiers. In the three-phase control rectifiers, we can see that exactly same only the thing is pulse numbers will change. Half wave and full wave, but input is a three-phase supply. In the single phase case, single pulse converter and two pulse converters will discuss, and three phase case, three pulse converter and six pulse converters. So once the pulse number increases, automatically magnitude will increase. And the significance of the freewheeling diode. So once if we use the freewheeling diode, or what is the effect of freewheeling diode? So it is across the load we will connect, as we discussed in the first unit, that is a power diode. So here we will use as a diode across the load to suppress the negative conduction, and automatically performance and efficiency is going to be improved. So these are the case, and another last topic of this unit is a dual converter. Because in the previous controllers, whether it is a single phase or a three phase, the based on the quadrant operation, we can say that single quadrant and two quadrant converters. But whenever you required all four quadrants, then we must use as a dual converter. So in that dual converter, two modes of operation. One is a circulating current mode of operation, another one is a non-circulating current mode of operation. So this is one important question. Dual converter, it is a also called as a four quadrant converter. Full converter is a two quadrant converter. Dual converter is a four quadrant converter. Semi converter is a one quadrant converter. So like this, based on the quadrant operation, based on the input supply, like that, based on the load, we can divide the classifications. So now this is the total unit. Now before going to mid exam, we need to complete first this one, single phase alone. That is a single phase control rectifier, half wave control and full wave control with the different loads, R load, RL load and RLD load and all. That is the syllabus for our mid exam. Now first 2 units already completed. I shared the material also. Just go through that. That is more than sufficient. And if you want any test books, you just refer it for your convenient author. And now the dual converter, the two modes, that will be the last topic of this unit. We'll see that normally DC power is obtained from motor generator setup. So this introduction also I told different methods are there to generate as a DC power. Now you can see that suppose motor generator setup is there, the x-axis is a field current and y-axis is a generated EMF. So this will be EG versus IF. So once the field current is increases, then automatically generated EMF will be increases. Once it reaches to the saturation, the EMF will be remains constant. So in between, you can see the variation. So you can able to get it as a variable DC voltage by make use of a motor generator setup, because this motor input you can connect it to the electrical and couple to the generator, Once motor is rotating, the generator will generate the EMF. To get variable voltages, generated EMF will generate, and variable voltage will be obtained by changing the excitation of a generator. So that way we can able to get it as a variable DCs. Now we can and also AC also available, supply is AC, then you need to get it as a DC power by means of a mercury arc rectifier or thyratron. So olden days they will use, before thyristor there is a thyratrons will be there, are also called as mercury arc rectifiers or mercury arc valves. So that will be used to convert AC to DC. But later on there is a thyristors invented, that lot of advancement in the semiconductor devices that will be convert AC to DC. Now we'll see the phase control rectifiers. It will convert AC to DC. It will convert fixed AC to the variable DC by using a thyristors. So now changing constant AC input voltage to the DC output voltage, that is the main function of a phase control rectifier. It will convert fixed AC to the variable DC by make use of a thyristor. In that process we have a lot of classifications. Any classification or any circuit, it will give AC to DC only, but depends on our requirement. We need to select which controller is preferable for that particular application, whether you want quadrant wise or you want output power wise, depends. So like that you can get it. In a phase control rectifier, the turn off AC supply voltage reverse bias it. So then we can see that thyristor will be turn off as AC supply voltage is reverse bias. That means during negative off cycle, thyristor will be turn off, or current pass through the device is to 0, then also thyristor is going to be 0. So anode current fall to the level of below holding current, it is nothing but a process of turn off the device, or current pass through the device below the holding current, then the device is going to be turn off. The commutation of a thyristor by supply voltage itself called as a natural commutation or a line commutation. Especially in the phase control rectifiers, we will use only the natural commutation or a line commutation. Both are same, only just line voltage make use to turn off the device, that's why line commutation, or naturally without using any additional circuit or commutating elements, the devices are going to turn off, that's why it is a natural commutation. Throughout this unit, whether it is a single phase or a three phase or a dual converters or anything, we will use only the natural commutation. The reason is input is AC supply. Whenever input is AC supply, automatically device is going to be turn off naturally. And the rectifiers need no commutation circuit, because here the AC is input, that's why we don't want any commutation circuit additionally. Simple, less expensive, and therefore widely used in industries where the controlled DC power is required. So whenever variable DCs are required, then we can go for as a rectifiers or a phase control rectifier. There is a another controller also available. There is a choppers. In that chopper we can able to control the DC voltage only. But why the choppers are not used in some applications? Because the chopper, to turn off the device, we required as a forced commutation. So for that it is a forced commutation techniques is required to turn off the device. But whereas in the phase control rectifier, we don't require any commutation circuit. That is the reason. And also another thing, for the rectifiers, if available source is AC, preferably we have AC supply, that you can connect it to the rectifiers. Whenever input is a DC, you can connect it to the choppers. And now, so many industrial applications controlled as a DC power. So that is such applications are steel rolling mills, paper mills, printing press, and textile mills. So these all DC drive applications we can use as a phase control rectifier, and traction system work on DC only. And then electromechanical, so that is a or electrochemical and electrometallurgical process, we can use the DC supplies. And then portable hand tool drives, that are, you can say, the drilling and all. So this type of application, and HVDC transmission, high voltage DC transmission, for all these we required as a rectifier, or it will convert AC to DC, or you can say that variable DCs are required. And as you are aware that classifications broadly, phase control rectifier classifying, there is a single phase control rectifier and three phase control rectifier. Again, single phase we can divide half wave control rectifier and full wave control rectifier. So similar fashion in the three phase also, half wave and full wave. But only thing is here, in a single phase half wave means one pulse converter. There is another different, because names are same, but only thing is based on the supply. This one is a one pulse converter. Full wave means it is a two pulse converter. And in case of three phase converter, half wave means it is a three pulse converter. And whereas full wave means it is a six pulse converter. So these are the available controllers classifications based on the pulse number, or based on the single phase and three phase we can classify half wave and full wave for both sides, but based on pulse number we can classify like this. And another, based on the load also, we can see that you can get first quadrant alone, or first and second quadrants, and then all four quadrants. So these are the based on the quadrant operation. So like this we can classify the controllers. And again, full controller we can divide midpoint converter and bridge converter. Difference between these two, midpoint and bridge converter, whereas in the midpoint converter, transformer, midpoint or center tap transformer is required. And bridge type, we don't require any transformer, directly we connect the devices in the form of a bridge, and you can connect input as a AC supply, and directly you can take it as a output as a DC. By changing the firing angle, output voltage is going to be controlled. So that is the bridge type. Anything, the process is same, only the circuit configuration. And see, the midpoint transformer is required, bridge converter we don't require any transformer. And these are the classifications. And again, bridge type we have as a two controllers, one is a semi converter, another one is a full converter. So this semi converter is only the first quadrant operation, irrespective of the load. Now you can see whether you connect R load or RL load, or anything RLE load. So there is a voltage, output voltage and output current remains in the positive, because of semi converter consisting of a freewheeling diodes. Whenever freewheeling diode is there across the load, there is negative voltage will not be obtained. That will forward bias the freewheeling diode, and device is going to be load terminals are short circuited, and voltage across the load will be zero, therefore it won't get any negative voltage. So that is the case of semi converter. And similarly, in case of full converter, you can see this, we can get first quadrant as well as the fourth quadrant operation. That means the voltage either get positive or negative. So this is either positive voltage or a negative voltage, depends upon your requirement. So here firing control you will change to get as a positive, anyhow that will come theory part. And if alpha is greater than 90, we'll get it as a negative. If exactly 90, output voltage will be 0. That is the scenario we can able to control. Similar fashion, three phase also, Bridge converter you can divide as a like this, semi converter and full converter. So same logic. This is the major classifications of your rectifier. And last topic, as I mentioned, there is a dual converter. So in a full controller, what we are obtaining, either first quadrant or fourth quadrant we are obtaining. But some application, if required all four quadrants, then what we want to do, instead of using only one full converter, you make use of a two fully controlled converter connected in anti-parallel will form as a dual converter. That is the major classifications. Now we'll see there is another classification in the case of single phase itself. We broadly divide single phase and three phase. Again, same thing based on the supply input. Single phase we have as a half wave or a one pulse converter, full wave or a two pulse converter. In a one pulse converter, we can have with freewheeling diode and without freewheeling diode. So what we want to notice is without using freewheeling diode, what is your performance? And with freewheeling diode, what is your performance? So like that, we can see that single phase we itself has one pulse converter, and in that we notice one is a without freewheeling diode, another one is a with freewheeling diode. So what is this freewheeling diode? Is simply as a diode connected across the load terminal. So whenever negative half cycle, if the load is RL load, there is a during positive half cycle energy will stored in a inductor that has to be dissipated. But once it is dissipated, they continue to conduct the device. So that's the reason we want to make use of a diode across the load. We'll make it as a voltage across 0 after pi. So that is purpose we will discuss with freewheeling diode and without freewheeling diode. And the two pulse converter, there is a midpoint type converter and bridge type converter. So again, bridge type is as usual semi converter. Another name for semi converter is a half controlled rectifier. So in exam point of view, you must know the difference between these two very well. Otherwise, you will get some mistakes, common mistakes. You can see that half control. Semi converter other name is a half control, whereas half wave, this one is a half wave. So half wave is a one pulse converter, half control is a two pulse converter. This is the major difference. This one is simple, one thyristor is there, here is a two thyristors are there, and there is a one pulse here, but semi converter is a two pulse, or in the three phase case says we can get it is a three pulse converter also if it is a three phase semi converter. So now as per our diagram, we can see here semi converter or half control is different with half wave. That is major. If I ask in exam explain the half control rectifier, many people will write half wave rectifier. That clarity must be remembered, especially this unit alone. And similarly full control converter. So these are the single phase classifications. Now we'll start this one. So today we'll finish it this portion. Half wave are also called as a single pulse converter with the R load, with different loads we'll see, and RL load, then RLE. So only what you want to know is RL on. That's all. Once if you know very small circuit R load, then RL load means what we have to do. RLE load means what we have to do. That difference only is required. Otherwise, everything is same. And after that, RLE load with freewheeling also we can able to connect across the load with freewheeling diode. If you add, then what is your response? So that is the complete one portion of the single phase control rectifier. We'll see that first question itself. That's what I mentioned here. This one is a single phase half wave control rectifier are also called as a one pulse converter. So half wave or one pulse converter. Now, what is the half wave rectifier? It is a just one thyristor source, then one. That's what we done that simulation also. No, there is a thyristor and then source, then load. So here we need to see different loads. So what is this? We can see first load is a R load. Then you replace R by RL. Then replace RL with freewheeling diode. One diode across the load. And then RLE load. So R and also connected to E like this. So this is the way we can able to get our response. Only you need to understand this question. Very simple, but throughout the unit is similar. Only small modification. Now we'll see the first one. Here all the cases explanation is fixed one during positive off cycle, that is 1 point, and during negative off cycle. That's all. So only these two things throughout all the classifications. Positive off cycle, what will happen? Thyristor is a forward bias. Thyristor is forward bias means it is ready to conduct. But when it will conduct? Whenever if we give the gate signal. The gate signal we can able to give from 0 to 180 degree. Anywhere you can give the gate signal. So now either at 0 itself we can give, and at 10 degree, 20 degree and so on. So what is the difference is, if you give gate signals initially, you will get more output. If you are delaying or you are waiting to conduct some delay or firing angle or a delay angle, during that instant you don't get any output because we are waiting for signal to turn on. So until that the device will be off state. As you are aware that all the waveforms, one blind thumb rule you remember. If you remember that, the waveforms also easy. What you want to do is output voltage across the device. For that two instants, what is that instant? On duration instant, off duration. So these are the two instants we have. So when the device is on, output voltage will be same as the source. When the device is open, output voltage will be 0. And when the device is on, voltage across the device is 0, and this will be as a source voltage. So this table, if you remember, very small table, just Vs0 and 0 Vs. So this one is a output voltage, second one is a voltage across the device. So these two things you apply this logic, whether it is on or off, you identify that. Now what I have to do, I am giving some firing pulse at an angle of some alpha. Then whenever firing pulse is given, immediately the resistor starts conducting. Now you can see here I am applying angle or firing angle at an angle of 30 degree or 20 degrees. Then the device starts conducting. Output will be same as the source. Now we can notice that what will happen, the current. So that is a current directions as well as the voltage, load current and all. The instant you can see the first line 0. The ball is from 0 onwards, it is gradually moving, that is a source. And now the gate pulses from 0 to alpha, no firing pulse, then output voltage will be 0 and output current also will be 0, and then voltage across the device is same as the source voltage because it is off state. Off state load voltage and source voltage are same. Now you can see, I mean during off state load voltage is 0, and then whatever it is voltage across device will be same as the source voltage. Now after that, once the device is on, what we are getting? It is same as the source voltage we drawn. And later on you can see here it is going like this, and then current and voltage waveforms are same, and voltage across the device will be 0 when the device is on. This is a fixed logic. What logic? I given small table. No, when the device is on, you check it. Device is on. Output voltage same as Vs and current also same as Vs by R. That means output by something load resistor, and voltage across the device is 0. This is for when the device is conducting. Now, what will happen later when the device is off state? How the device is going to be off? Because supply is 0, natural 0. By applying forced commutation, device is going to be turned off. Then all the devices will be off. Now output voltage 0, current is 0, no firing pulses, voltage across the device is not 0. Why? Because you can see here this point voltage across the device. One terminal is directly connected to source, other terminal also through resistor it is connected to source. So then voltage across that device is same as that of the source voltage. So that's why after pi we will get it as a same as the source voltage. Now that is the circuit operation, and now you see the derivation. What is the derivation? You need to derive all the quantities. What are the quantities? Average voltage, average current, RMS voltage, RMS current, then ripple factor, form factor, input, output, powers, then efficiency, transformer we are using. Suppose if connect as a transformer instead of directly here, you can connect to through transformer also. There is a primary, this one, and here you can connect as a secondary. So now when the transformer is there, here you can connect as a source. So now transformer utilization factor. So all the parameters you can derive from the plots. Now you can see first one is average output voltage. So what is the average voltage expression? Initially it is 0, device is not on, then it will be turn on. This is alpha, this is pi. Then you can get it as a during negative off cycle it is 0, and again pi plus alpha will get same as the input voltage. So after pi there is a natural commutation from pi to pi plus alpha. You will get it as a 0, and then 2 pi plus alpha you get same as the source voltage. So this is the output voltage. Now alpha to pi, pi to 2 pi, here up to 2 pi, and this is a 2 pi plus alpha. And what is the your integration? So now one full cycle, how many pulse we have? 1 pulse, because it is 1 pulse cannot 1 by 2 pi. Limits are alpha to pi. Your output is Vm sine omega t. So this is your output. If we integrate that, then what will happen? Vm by 2 pi. Integral sign will give minus cos omega t. Limits are important. Here limits are alpha to pi. So if you do that, then cos pi is minus 1 already plus, then 1 plus cos alpha. So Vm by 2 pi into 1 plus cos alpha. So this is the case output voltage. So similarly, you can see here just same thing, 1 by 2 pi, 0 to pi. One full cycle I have to integrate, but our limits are what? Alpha to pi only output is there, rest portions are 0. So that's why I made it as alpha to pi. And final output will be Vm by 2 pi into 1 plus cos alpha. Now, I want maximum output voltage. When can I get the maximum output voltage? If you put alpha is equal to 0. So if I put alpha is equal to 0 here, then cos 0 is 1. 1 plus 1, 2. So 2 will get cancelled. So now it is very important question. They may ask at what instant maximum output voltage will be obtained. VDC, that is equal to alpha is 0, cos 0 is 1, 2 will get cancelled, Vm by pi. At alpha is equal to 0, that's all. Simply at alpha is equal to 0 degrees. Because no delay, no, you will get more output voltage. That is only the maximum permissible output voltage. Then Maximum means just alpha is 0, you get Vm by pi. Third one, average output current. Once if you know the voltage, you will get as a current. Current IDC is equal to VDC by R. So IDC is equal to VDC by R. And RMS output voltage, you can see that same average output voltage only, you just square it and root it. So this will give like this. 1 by 2 pi integral alpha to 2 pi means one full cycle only, but rest portions are zeros, then we can use only alpha to pi integration. So just alpha to pi Vm square sine square omega t whole power 1 by 2. So this is the limits we can get it. So now Vrms is equal to 1 by 2 pi alpha to pi Vm square sine square omega t d omega t whole power 1 by 2. Now we can see Vm square I am taking out. In that we'll get it as a Vm sine square omega t I can write 1 minus cos 2 omega t by 2, and 2 also will take it out. Then what will happen? 4 pi will be there, and 1 into d omega t, that will give omega t minus, here also minus sine 2 omega t. So integral, integral cos 2 omega t, I can write it as a sine 2 omega t by 2, and the limits are alpha to pi. If we substitute that, we'll get it as a, what is the Vrms? Vrms of half wave or one pulse converter with R load, that will give Vm into pi minus alpha by 4 pi plus sine 2 alpha by 8 pi whole power 1 by 2. So this is the Vrms. Now we will get the Vrms current. You can see that IRMS current. Once if you know the RMS voltage, you will get as a RMS current. Simply you can make it as a IRMS, that is equal to VRMS divided by R. Like here, what is the average output current? IDC by R. Now here we can simply IRMS by R. So that will give as a what we call it as a RMS current. And next one we can see what is the variations. So here variations are alpha versus output voltage. So as I said earlier, the firing angle range is 0 to 180 degrees. So either if you put alpha is 0, what you can get? Alpha is 0 means you will get it as a maximum output voltage. If alpha is equal to 30 degrees, then you will get it as a formula only. Just VDC formula, what we have is Vm by 2 pi into 1 plus cos alpha. This is the formula. Now put it alpha is 0, cos 0. So then 2 to get cancelled, Vm by pi. And alpha is 30 degrees. Then cos 30 root 3 by 2 plus 1. So this is the factor we multiply. We will get it as a output voltage. In terms of percentage, you can see that alpha is 0 means 100% will get, and alpha is 30, 90%, 93%, then 60, then 90 and so on. If you make it alpha is equal to 180 degrees, you get it as a 0. So from this, what is our analysis? By increasing the alpha, you can see that 0, 30 and so on. By increasing the alpha value, your output voltage is going to be decreases. Now you can see 100, then 90, 75, 50 and so on, finally it reaches as a 0. So alpha increases, your VDC going to be decreases. So this is the way we can able to get it as a alpha versus average output voltage. That's what waveform also you can see. By x-axis is alpha 0 to 180 degrees, and the y-axis is a output. You are getting gradually decreasing, and finally it reaches as a 0. So this is the single phase up control converter with R load. And another parameters RMS output current VRMS by IR. So that will give as IRMS. And then power at load side. So that is a output power at a load side. So PDC. PDC is a output power, is a DC supply. That's why we'll get PDC is equal to VDC into IDC. You multiply that, we'll get it as output power. You know what is the VDC? You know what is the IDC? VDC is nothing but a Vm by 2 pi into 1 plus cos alpha, and IDC is nothing but a VDC by R. That simplification that will give as a PDC, output power, and power delivered to the load. So from AC supply. So that means IRMS into VRMS, or VRMS into IRMS, both are same. So just power delivered to the load, multiplication of VRMS into IRMS. That will give as a AC power. Then what is the efficiency? I know output, I know input, then you will get it as a efficiency, output by input. So P or can say that controller efficiency, we can represent PDC by PAC. So that will give as a efficiency of the controller. And the input power factor. So power factor formula is power delivered to the load divided by volt amperes. So you can see that power delivered to the load formula is already known to you. VRMS into IRMS divided by volt amperes. So volt amperes Vs, and then current, that is a Is, Vs into Is. So Vs, Is and IRMS will get cancelled, and finally power factor is nothing but a VRMS by Vs. This is a important, what is the input power factor of a controller, because power factor will be the major role. Now we can see that VRMS by Vs. Vs is a supply voltage. VRMS we will calculate it 1 by 2 pi integral alpha to pi Vm square sin square omega to whole power 1 by 2. If you simplify that, we'll get it as a VRMS, and Vs as usual supply. And then form factor. So form factor is a VRMS by VDC. And then ripple factor, root of form factor square minus 1. So these are all general formulas. And why I am telling this, all other controllers, so except VDC expression and then VRMS, these two, except these two, all the things are formulas only. In any controller, whether if you change the load or you change the controller, VDC will change, VRMS will be changed. So once this VDC and VRMS both is changed, then we can easily get it what is the other quantities. Other quantities are formulas only, no? IRMS, PDC, efficiency, power delivered to the load, and power factor. So all these things are formulas. Only these two will differ. So other than this, everything is formula. That's why I am listing out these formulas. After that, these things will not be repeated further, because this is all formulas only. No? What you want to do is you find VDC and find VRMS. Rest of the formulas direct substitutions. And then circuit turn off time, when the device is going to be turn off. So that will be omega Tc is equal to pi, because it is a natural commutation, that to R load omega T at pi, the device is going to be turn off. That's why the T is equal to Tc will represent, then Tc is equal to pi by omega. This is a circuit turn off time. Another one is a transformer utilization factor, because we used as a transformer in the input. If you are not used, not required, let it be. It is a transformer, and then that you can connect it to the thyristor, and then there is a load. So that will give as a transformer utilization factor. You have to find what is the transformer utilization factor. That is the formula PDC by volt ampere rating, or volt kVA rating, or you can say the transformer rating. So PDC, already known that PDC into IDC divided by volt ampere. So that will give as a transformer utilization factor. And peak inverse voltage. So what is the peak inverse voltage means? When the device is off state, you can see that there is a supply and device is open. Let it be under open state. What is the reverse voltage or during negative off cycle? How much maximum voltage it will appear across this Supply is Vm sin omega t, no? And once the device is off state, the reverse voltage applied across this, because it is open, then that magnitude is a Vm. So that's why inverse voltage. So peak inverse voltage, the maximum voltage applied across the device when the device is off state, you can see that it is a Vm, or you can say peak inverse voltage or reverse voltage, or you can say that. And these are the quantities. And now from later on, whatever we used for the loads, other loads also, formulas will not change. Only change will be integration limits, where it will start and where it will end for the conduction. Once if we clear that, only substitution is VDC expression, VRMS expression. The remaining all formulas. Now we'll see, instead of R load, what I will do? I will use RL load. So load will change. Now you can see same circuit only. That's why if you are aware that previous two slides, one is a power circuit and waveform, second one is a derivation part. So if you just thorough that two slides, and rest will only the modification. So that modification is with logic, that is very simple word, and we'll see that now. So what is the different here? First circuit different is, instead of R, I made it as RL. That's all. So now the circuit is over. Then waveforms modification. What is the modification of waveform? Earlier, device conducting alpha to pi, started at alpha, ended at pi. Because at pi, supply voltage is 0, load voltage also 0, and current also 0 because of the resistive. Now thyristor will be turned off at pi. But now during positive half cycle, say at an angle of alpha, I am giving pulse to the thyristor. Then we can see R and L. This is a plus and minus. The energy will store the inductor in this polarities. This you can see supply is given, then it goes to R and goes to the L. Then what will happen? Some energy stored in a inductor. So energy stored in a inductor. After that, once it reaches to the pi, the supply voltage will be 0. From there onwards, polarities will reverse. Now, whatever energy stored in an inductor, that polarities will reverse. Now, there is energy in an inductor, it is going to be dissipated. What is the path for dissipation? L plus. Now the polarities are reversed. This is a plus, and it goes to the supply, and again it goes to the thyristor, then R, then L minus. So this is the thing we can able to pass. That means same direction current is passing through the same thyristor. Then what will happen? Thyristor will conduct. Once thyristor is on, what is our output voltage according to our previous logic? Thyristor is on, output voltage same as source. But what is the source after pi? Negative. That's why you will get it as a negative. Now we'll see supply. This is the input. Now at an angle of alpha, I given firing pulse. Let it be I given pulse at this instant. Then what is our output now? From that point onwards, it will start conducting. Then it will get it like this at pi. And now from pi onwards, load voltage 0, source voltage 0, but current is not 0. This is a voltage. Now I will represent the current. Just carefully observe this. We are starting this point. Before that current also 0. Now current will be gradually rising because it is storing the energy. Current will be rising. And after that, once it reaches to the pi, there is a polarities will reverse. Earlier upper side is plus, lower side is minus. Now upper side is minus, lower side is plus, because energy dissipation is going to be takes place. That's why this will be gradually decreases the current. So now during that thyristor is on. If thyristor is on, what will happen? The source voltage same as the load voltage. What is the source? Up to some duration. This will be like this. Now your output will be like this. Over. So what is the difference between R load and RL load now? R load, the device is turn off at pi, but RL load device will continue to conduct some more time because of the energy stored in a inductor. Let assume that after some instant the device is completely turned off. If device is completely turned off, then what will happen? Current will be reaches to 0. If current is reaches to 0, device will be open. At this point, device will be open. So this will be open. Once it is open, output voltage will be 0 and current also will be 0. That's all. So this is only the different. Now we'll see the waveform. Now notice the previous waveform and this waveform. Only one different in the circuit time. Here you add the L, and this case, output waveform's case, earlier this will be 0 like this, because it turn off at pi, but now it will continue to conduct up to beta. This is only the different in the output voltage waveform. And current waveform, 0 to pi, it is gradually rising and then it is decreasing gradually. So that will be as a up to beta. Beta or beta is equal to pi plus alpha if it is a large inductor. That anyhow in full wave you can clearly notice that. Here discontinuous mode and continuous mode of operation will be there in the case of full wave rectifier. If I call it as a discontinuous, the current will be continue to conduct up to beta. Beta value is less than pi plus alpha. That we call it as a discontinuous. If beta is equal to pi plus alpha, then it is a continuous. This also you can remember. So that way, and now voltage across the device, everything same logic. What we noticed that 0 to alpha, device is off state. That's why voltage across the device same as the source, and then load current is 0 because open. Output voltage also 0 because it is open. And once it is conducting from alpha onwards, how long it will conduct? Up to alpha to beta. Now current also will be present up to alpha to beta. This duration I call it as a conduction angle, because the device is conduct during that instant. That's why that instant I call it as a conduction angle. The instant at which device starts conducting is a firing angle, and then conduction angle means the device starts conducting from alpha to beta or a pi plus alpha, the duration. The or current extends to the 0, that point we call it as a conduction. From starting conduction angle means alpha will be fired the device, from that point to current is extends to 0. So that duration I call it as a conduction angle. And now once the beta reaches current is 0, the device will be open, and this is a positive half cycle explanation. And during negative half cycle, what will happen? We can notice here, negative half cycle, there is a output voltage will be 0. Why? Because the device is already turned off at beta, and during negative half cycle, this diode is a, thyristor is a reverse bias. Thyristor is reverse bias means it won't conduct, that will be open. Then the output voltage will be 0 and current also will be 0. Then what about voltage across the device? It is same as the source voltage. So that will be source up to beta it is conducting, no, from there onwards, and it will become source voltage until next 2 pi plus alpha, because 2 pi plus alpha next cycle is going to be repeated, because 2 pi again firing pulse, whatever this pulse, if you want you can add one row here, you can apply the firing pulse during positive half cycle. This also you can do because pulse will be available here. Negative half cycle reverse bias, that's why we don't require any firing pulse. So here you can give pulse like that. Whenever positive half cycle is there, you can give firing pulse, that is a Ig. That will be at alpha instant. This will be 2 pi plus alpha. This is a 4 pi plus alpha. So all the positive half cycle give the firing pulse, will get it as output. Now once the explanation is over, next what you have to find the derivation part. So for output voltage expression, the derivation you can see that limits as usual only one pulse in the output, 1 by 2 pi. And what is the limits? Start with the alpha, end with beta. That's all. Other part is 0 anyhow. So this is only the change in the derivation part. So Vm sine omega t d omega t. So this is the average output voltage expression VDC, or you can say that. Earlier it was, instead of beta we used as a pi for R load. So for RL load case there is a continuous mode of operation and discontinuous mode of operation, two things are there. For continuous mode of operation you can make it beta replaced by pi plus alpha. You will get average output voltage for continuous mode of operation, or if you use beta you will get average expression for discontinuous. Same thing, you just square it whole power 1 by 2, you will get it as a VRMS. That's all. Once if you know VDC, VRMS, you can get PDC, PAC, efficiency, maximum output voltage, and transformer utilization factor, or form factor, ripple factor, everything, power factor. All the things are formula, only different is VDC and VRMS. So in that I will show the derivation part also. Now this is, if you do the simulation you will get the same waveform, whatever theory waveform will be there, you will get same thing. You can try for that, I already explained you in the previous lab. And now at what instant the beta expression, I want to know when it is going to be current is 0, because our current waveform, you can see our voltage waveform, it start with alpha and with beta. This is the waveform, and that is a voltage waveform. If you want, you can draw current waveform also. This is a current waveform. So now we can notice that this is the alpha instant and this one is a beta instant. Now we can derive our expression, voltage equation. When the device is turned on, what is our voltage equation? Vm sin omega t is equal to Ri plus Ldi by dt. From this apply particular integral and complementary function, and then Laplace, inverse Laplace, whatever, any mechanism you can apply, and we will get Is steady state and transient. That way also you can do. So that is a Vm by Z sin omega t minus phi for steady state, and phi is tan inverse x by r, and then we can see the transient component, that is a I r or it, you can see that Ri plus Ldi by dt is equal to 0. So sum of this steady state and transient will give as a what is the I of t. So now transient expression, some constant, whether k or a, any notation you can follow. So k into e power minus r by L into t, or a into e power. So you add these two. Is plus it is equal to I. So your expression is this: Vm sin omega t is equal to Ri plus Ldi by dt, and from that I is equal to, what is I naught? Output current, Is plus it, Vm by Z sin omega t minus phi plus a into e power minus r by. Whether you got the output current value from this? No, because we don't know what is the value of A. All other parameters are known. I know Vm, I know Z because R load and L load is known to you, so you know the Z, and then angle also know, tan inverse x by r value, everything is known, only except constant. How will you get the constant? By substituting initial condition. So what is the first initial condition? I drawn no earlier. So this is the voltage waveform. What is first initial condition? Omega t x-axis. Omega t is equal to alpha. What is the current? Your current waveform will be like this. Current is equal to 0 initially. Omega t is equal to alpha. I is equal to 0. I naught is equal to 0 at omega t is equal to alpha. You substitute that in this equation. Now, if you substitute that, you can see that omega t is equal to alpha, current I is equal to 0 if we substitute. So just 0, and what is unknown parameter? A into e power minus r, because t will get it alpha by omega, because omega t is alpha, from that t is known to you and a value is known to you. Once a is known, where you have to substitute? In our output expression. What is our output expression? I naught is equal to Vm by Z sin omega t minus phi plus a into e power minus R by L into T. This is our output expression. But now I know what is A. This is the A. And substitute that A value here and take it common parameter. Here also Vm by Z and here also Vm by Z. You just take a common Vm by Z. So now you simplify that. We'll get it as a I naught expression. So in that again another initial condition is there. At omega t is equal to beta. What is the current? Omega t is equal to beta. Current is equal to 0. Because in the waveform it will start like this. It is ended like this. No, the current waveform will be like this. So this is a omega t is equal to beta. Current will be 0. At omega t is alpha also current is 0. At beta also current is 0. So just substitute that also. Omega t is equal to beta. Current I is equal to 0. So from this you will get it expression for beta expression. This I call it as a beta expression. Now you use that our iterative process to finally find what is the beta value, because all other formulas are values are known. You will get the beta. So now once if you know the beta means that angle the current is going to be 0. So that is one small derivation for beta expression. That's what I mentioned here. There is a can be solved by obtaining the value of extension angle beta and the output voltage is given. So now we'll see the output expression. So that is only the beta expression. Now I know the angle. Later if we substitute that angle here, we'll get it directly what is the value of output voltage. Only the change is previous R load and RL load changes here is a pi. You make use of a pi. So alpha to pi Vm sin omega t d omega t. So that will give as a Vm by 2 pi into cos alpha minus cos beta. And then if it is a continuous mode, what you will do, instead of beta you make use of a pi plus alpha. That's all, you will get it as a continuous mode of operation. Now we will get continuous Vm by 2 pi sin omega t will give minus cos omega t alpha to pi plus alpha. So now you can get it Vm by 2 pi. So here cos pi plus alpha will give as a cos alpha and plus cos alpha, that will give as a 2 cos alpha. So now 2 get cancelled out. So your continuous mode of operation Vm by pi into cos alpha. This is for VDC. What is that? For RL load. And what is R load, you notice? VDC, that is equal to Vm by 2 pi into 1 plus cos alpha. So if you put different values of alpha, which load will give more output voltage? R load or RL load? Because if you put alpha is equal to something 0 degrees is same, and you make it as alpha is equal to 30 degrees for R load case and RL load case. Obviously R load will give more output voltage than the RL load. The reason is, you can see the waveform. I will show that waveform in the previous slide. Here you can see the negative voltage is obtained, whereas I will draw two waveforms. For R load waveform is like this, and RL load waveform will be like this. That means what? You are not getting 0, just whatever magnitude is here and here is same, but later on there is a negative duration is there, but here nothing, just it is a 0. So if you take average, automatically you will get it as a average output voltage will be less in case of R, whereas average output voltage is more in case of R load. Even though controller is same, alpha value is same, but because of the inductor you are getting as a less output voltage, and also in turn because of you are getting as a negative voltage in the load side, after pi conduction is taking place. That is the reason we are getting as a negative voltage, then average, or you can say that automatically will reduces. So that is the difference. Now we'll see how to overcome by make use of in the RL load case is completed. So just we derived that voltage expression, and this is a current expression. As usual, this divided by R will give as a average current or load current. Now RMS means same, this whatever average expression is there, square it whole power 1 by 2, that will give as a RMS. Then you can see circuit turn off time as usual 2 pi omega t is equal to 2 pi minus beta, because this waveform based on waveform only we are getting. Now this is the conduction, so it is started at alpha, it is beta, and then it will be 0. So if we consider up to 2 pi, so what is this instant? I want to know when the current is going to be 0. Omega t is equal to 2 pi minus beta. At this point it is going to be 0 current. So current waveform Fedra like this. So then what is this turn of time? So omega t x-axis, so this total I call it as a beta, and then total period is 2 pi period. 2 pi minus beta will give as a turn of time. So from this TC circuit turn of time 2 pi minus beta by omega over. So that will be as a TC. So this is a circuit turn of time. And average output voltage for continuous mode of operation. What is continuous mode? I told now instead of beta you replace by pi plus alpha. Now here three things you remember. For R load, limits are alpha to pi, and RL load limits are alpha to beta for discontinuous, and for continuous alpha to pi plus alpha. This is the limit. So now we will get VDC is equal to Vm by pi into cos alpha. Similarly RMS as usual, square it whole power 1 by 2, and the limits are alpha to pi plus alpha. You will get this expression. Now if you remember previous average and this RMS and this RMS, only small difference will be there. The limits alpha to pi plus alpha, earlier alpha to pi for R load. And now what is the difference? Now we noticed one thing, average output voltage is going to be decreases because of what? Negative conduction. So exact same circuit what I used as a freewheeling diode, that's it. So if I use freewheeling diode, what will happen in the operation? During positive cycle it goes like this, it will store energy plus and minus, and while it is dissipating, now we can see storing is plus and minus, and dissipation this is minus and this is plus, and minus is connected to cathode, plus is connected to anode. So it will be across the load will be short circuited. So across the load it will be short circuited, then output voltage will be 0. You don't get any negative voltage here because after pi device is not conducting. Only freewheeling diode is conducting but not thyristor. So that's why source will be isolated. That is the reason you don't get any negative voltage. Earlier, if freewheeling diode is not there, so what will happen? You can see that there is a conduction. If this freewheeling diode is conducting, then output voltage will be 0 because short circuit across the load. But once you can notice that if this is not there, so if this one is not there, freewheeling diode is not there, thyristor, this energy will passes through the thyristor. That's why thyristor is conducting, you are getting negative voltage. But now to avoid that negative conduction, you are creating another path through the diode. Then what will happen? This current will passes through the diode. So therefore, current will be present. Whatever energy stored in this inductor, if that energy is passing through diode rather than the thyristor. That's why diode current will be present, but this portion is a 0. So diode current will be present, but thyristor is off state. That's why it will be 0. So that is the difference. Now what is the advantage by using that? Even though if you use as RL load, your expression is same as the R load expression because waveform is same. Now what is the limits? VDC, that is equal to what I can get? 1 by 2 pi, because waveform is same, expression also same, alpha to pi only, Vm sin omega t. So if alpha to pi Vm sin omega t, then what you can get it? Vm by 2 pi integral sin omega t will go minus cos omega t, that is as usual of same as R load. So even though if you use RL load, you will get the same output voltage of R load. That by make use of a prevailing load. And also another function is what? It is suppressing the negative conduction. So obviously it will improve the power factor instead of getting negative. So this is negative is feedback to the source side. Means we are drawing the reactive power from the source, but now it is not required because of the diode. So therefore power factor is going to be improved. So that is the advantage or effect of a prevailing load. If question asked instead of direct this question, explain single phase half controlled or half wave controlled rectifier with RL load and prevailing diode, or another version they ask the question, explain the effect of prevailing diode. So effect of prevailing diode, use this circuit and this is the waveforms, and then derive the expression for VDC and then write the impressions. What is the impression? We are avoiding the negative conduction. Current waveform will be improved. Now you can see that earlier current waveform and this waveform is a little bit in the ripple will be minimum compared to the previous one. Current waveform will be improved and negative conduction is not there and power factor will be improved, and these are the advantages or effect of the prevailing load. So that way we can conclude the effect of the prevailing load. So that's what in the next class we'll see RLE load. And if you have any doubt, you can ask me. Then you can leave. If you don't have doubts, you can leave.